Condition for deriving this equation is that work done in moving an object is stored as kinetic energy. So we are considering an object in motion and to find the work done to move the same object. Consider an object of mass m initially at rest. Initially at rest means the initial velocity of the object remains as 0. Consider an object initially at rest. When a force F is applied to the body, the object will move with a velocity v. The object will move with a velocity v. This is the condition we are required for deriving half mv square. That is the equation for kinetic energy. Now we have to find the work done in moving this object. We know that work done W is equal to force into displacement. That is equal to by Newton's second law of motion. We already discussed in this topic in second chapter, force and laws of motion. There we have Newton's second law of motion and mathematical formulation of second law. From mathematical formulation, we clearly know that force F is equal to mass into acceleration, that is ma. Therefore, I am substituting F as mass into acceleration ma into displacement s. Now we get the equation W is equal to ma into s. Then by third equation of motion, the third equation of motion was also discussed in the first chapter, motion. The third equation of motion is v square is equal to u square plus 2s. I am just shifting this u square to the left hand side, then v square minus u square is equal to 2s. From this equation, I am finding s as s is equal to v square minus u square by 2a. Okay. Here in our concept, the object is initially at a rest. The object is initially at a rest means initial velocity of the object is 0. Therefore, we can put u as 0. That is s is equal to v square by 2a. Since u is 0. We already know that our object initially at a rest, therefore initial velocity is 0. Then we can cut this term u square, this 0. Then s is equal to v square by 2a. Just substitute this value in the equation for work. We are having equation of work as W is equal to ma into s. Now we get s as s is equal to v square by 2a. Therefore, W can be written as W is equal to ma into v square by 2a. Look here, we are having an acceleration term a in the numerator and the same term in the denominator. Then we can cancel a in both numerator and denominator. Both the a got cancels each other. Remaining W is equal to mv square by 2 and can be written as W is equal to half mv square. Now we get the equation for work done in moving the object. We already said that work done in moving an object is stored as kinetic energy. That means this work done is stored as kinetic energy. Therefore, kinetic energy can be written as half mv square. Therefore, kinetic energy can be written as kinetic energy is equal to half mv square. This is our required equation. This is our required equation. We are deriving this equation. Now we complete the first form of energy. That means when considering the mechanical energy of an object, the mechanical energy simply means total energy of kinetic and potential forms. Among that, we just discussed about kinetic energy. It is the energy possessed by virtue of motion, and the equation is half mv square. Now you understand how we derive the equation for kinetic energy. Now we can move to the second one, potential energy. Potential energy is the energy possessed by virtue of its position or state of strain. Due to an object's position or state of strain, the energy possessed is potential energy. For example, a flower pot which is in the upper part of the terrace, or the water stored in a dam. In the cases, the flower pot in the terrace, it gets energy due to its position. It is at a height from the ground level. Therefore, it gets its energy due to its position. In the second condition, water stored in a dam, it is in a strained state. Therefore, it gets energy due to its state of strain. Or when we are considering a spring or rubber band in a stretched state, it is also in a state of strain and it gets energy due to its state of strain. In all these cases, the object gets energy due to its position or state of strain. Then that energy is called as potential energy. Then that energy is called as potential energy. That means the energy possessed by a body, the energy possessed by a body by virtue of its position or state of strain. This is what potential energy. It is the energy possessed by virtue of its position or state of strain. Like the similar way, when we are explaining kinetic energy, we derive what the equation for kinetic energy is. That is, kinetic energy is equal to half mv square. Like the similar way, we have to derive what's the equation for potential energy. And I am going to derive the potential energy stored in an object placed at a height. Potential energy stored in an object placed at a height. This is the ground level. And we are having an object of mass m at the ground level. And when we shift the same object towards a height h, then what will be the potential energy stored in the object? To find the potential energy stored in this object, we have to find the work done in pulling or pushing or making the object or taking the object to a height h. The work done in displacing the object to a height h is stored as potential energy. This is the initial condition, and we are going to find the work done in displacing the object to a height h. Now we have to find the work done. We already know that work done W is equal to force into displacement. That is W is